Okay, I hear the recording in progress. So share the screen. Okay. Now, some of you may have noticed the last couple of times, including the test day, I got kicked out after 40 minutes. So that being the case, I believe the 40-minute count starts as soon as I log on, not when I press record. So that being the case, I will try to log on right at 8:10 or maybe slightly after 8:10. Normally I try to join a little bit early, but I notice when I join early, the count already starts. So that's why it seems to be a 40-minute limit. I think I found a way around it, but I'm not sure. So I guess we'll find out. So that being the case, if I get kicked out in 40 minutes, I will join right at 10 after or slightly after 10 after. Then at least I have the full 40 minutes for lecture, hopefully, in case we get bumped out, but we'll see how it goes. Okay, you all got your exams back, hopefully. If you did not get your exam email back from me, then tell me right away. And I sent out the solutions over the weekend also. So everybody should have their exam 3 scores, provided you submitted an exam and the homework. And I sent a video. Okay, so if you didn't get it, let me know. You get to drop one exam. Remember, one exam gets to be dropped. Our next exam is already on Friday the 29th. And then there's quote unquote only one more chapter, but that last chapter is a long one. Okay, so our next exam is 10-1, which I've already finished. 10-2, 10-3, 10-4, and 10-5. Okay, before I go on to 10.2, 10.3 is in something called polar coordinates and polar graphs, and part of 10.4. There is something, special kind of graph paper called polar graph paper that you need to get. And I want you to use exactly mine. So I will not accept as full credit any version of polar graph paper that isn't the one that I have pre-approved, so to speak, to make it fair on everybody and the calculations are equal. Okay, let me take a moment as to how to get that, but I'll send on Canvas announcements. I'll send a link as to where to find this particular polar graph paper. Okay, so again, we'll need that for section 3. And I think a fair estimate is that you're going to need about 20 of them, 20 polar graph papers. So you have to print one out and then copy the rest, or just print 20 out directly, however you do it. But polar graph paper. So let me show you the polar graph paper right now. And this is being recorded, so you can get that. So I have to stop the share here and do another screen share as to how to get that. So let me see how I can do that. So let me just get to any screen here. Okay, so just bear with me. Okay, so okay. No, I don't want the whiteboard. Starting up again. Sorry, this might be a while. I can't seem to get it. Oh well. That is a. Okay. Well, I'll have to share with you how to get that. But what the polar graph paper looks like, that I want you to get, is this. So let me go back to sharing the screen where I was. And you can find it. Okay, so polar graph paper looks something like this. You can find it under mathbits.com. Mathbits.com. You would scroll down to find it, but I think I'll give you the URL for that on Canvas announcements. And you must use this very particular kind, so to be fair on everybody. You'll notice that these are marked off in 15-degree increments. How do I know it's 15 degrees? Well, this is 0. This is 90 degrees. And if you count 1, 2, 3, 4, 5, 6. So 90 divided by 6 is 15 degrees. There are 14 concentric circles. So key things that are here. So 15-degree marks. And there are 14 circles. I know 14 is not a very convenient number, but it's the best that we've got, that, in my opinion. It's a full sheet. Okay, so if you look under mathbits.com and look under graph paper, you can find this very graph paper, but I'll try to give you the URL for that. And you'll need about 20 total for the semester. Okay, every 15 degrees, 15, 30, 45, 60, 75, 90. Okay. And there's 14 concentric circles. If you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 circles. Okay, everybody must use the same paper so I can grade everybody fairly. So if you do not use this graph paper, I may decide to give you less credit or no credit at all. Because part of the calculation involves, you know, how to divide up the circles and so forth. Okay, so this is called polar graph paper. Polar graph paper. And you'll need about 20, depending on how good you are. If you never make a mistake, you can get by with less, but if you're like me and you make mistakes, sometimes you'll need a few more for this assignment and the final exam combined. Okay. All right, so again, mathbits.com is where you can find it. I'll try to send a URL as to where you can get this thing. Okay. All right, so that'll be for section 3, which we're not doing yet. So you have a couple days to do it. On schedule, make this a little bit bigger here. And so we may start this on Wednesday, I suppose. And Wednesday or Thursday. Okay, let me check the chat. Yeah, I think somebody got, somebody put that. Is that the one? I can't tell right away. It looks like it might be the one. Okay, but I'll send the link and I think you have it correct. Okay, so thank you for sharing that. Yeah. All right. Okay, 10.2. Remember, I've already finished 10.1. So look back in the notes for 10.1. So remember, I'm on this side of the paper now. And by the way, that now tells you we're more than halfway through the course, right? Because all the semester I was on this side of the paper. Now we're on this side of the paper. So once we're on this side of the paper, you know we're more than halfway, right? So we're getting there. We're getting close to the end of the course, I suppose is the way to say it. Okay, so 10.2, a long time ago. I actually went over what you needed for this. Okay, so where were we? 10.1, parametric equations, right? X is a function of t, y is a function of t or theta. You can plot t versus x, t versus y, and then plot x and y as usual. And t can be thought of as a passage of time. Now we're going to do calculus with it. And I alluded to this very briefly before we had to stop and take the test. So 10.2, calculus with parametric curves, page 649. How do I take derivatives? Okay, so box number 1, dy dx is dy dt divided by dx dt if dx dt is not equal to 0. Okay. And this is a variation of the chain rule using the Leibniz notation from Calc 1, right? dy dt is dy dx, dx dt. It kind of looks like you can just cancel out the dx's, right? If you cancel the dx's, it says dy dt. Divide both sides by dx dt, and you get this. Okay, so put this in your next cheat sheet. There's a formula for dy dx, dy dt divided by dx dt. For the second derivative, and I don't know why the author didn't box this out, but here it is. D squared y over dx squared, second derivative. It means d dx of dy dt. A little bit of, it's hard for me to do this without the book falling off the table here. Sort of the rationale behind it. If I just cover this. Okay, second derivative means the derivative with respect to x of dy dx. Okay, so there it is, d of dy dx with respect to x, and it's almost like divide top and bottom by dt. So there it is. Okay. It's d dt of dy dx divided by dx dt. Now, this might look kind of scary, but it's not so scary as you might think. This dy dx, it's the answer you got from over here. And then dx dt you already computed. Okay, dx dt is back here. So you're just going to copy whatever you got over here. Okay, so from this stage, you need a dy dt, dx dt, you divide. When you get to this whole symbol might look scary, but it's not really that scary, and I'll show you once we get to it. You take the derivative of this answer and divide it by dx dt, which you already computed over here. Okay. All right, and then the other formula we might need is for arc length, page 653. Put this on your next formula sheet. Arc length. So didn't we already do arc length? Yes, that was if you have y is a function of x, or x is a function of y. Now you have x and y as a function of a third parameter, t. So it's almost like this, the logic. Okay, so square root of dx squared plus dy squared, that's basically the hypotenuse, right? Little change in arc length, square root of dx squared plus dy squared. And then I multiply by dt outside and divide by dt squared inside. So that's equivalent, algebraically, right? So there we go. Square root of dx dt squared plus dy dt squared dt. All right. And now we're ready. Okay, so 10.2, start showing you some stuff. Let's see, 1 to 19 odd, 25, 41, 42, 45. So I got to go up to 45. Okay, so page 655, for those of you who don't have the book and aren't getting it. Whoops. Let's see more there. Once again, anytime the author has a graphing calculator icon, you can ignore that part. And some more here, trying to get this into focus properly. A little bit more. Okay, how far do we have to go? Up to 45. So where is 45? Here we are. Yeah, find the exact length of the curve. So there we go. Okay. So on to some problems. Find the derivative. Okay, so 10.2. Number 1, find dy dx. X is t over 1 plus t, y equals square root of 1 plus t, or whatever it happens to be. It's fairly straightforward. So by formula, what is dy dx? That's the normal rate of change of y with respect to x, dy dx. So it's dy dt divided by dx dt. So dy dt, 1/2, 1 plus t to negative half. Dx dt looks like I do the quotient rule. Bottom times the derivative of the top, which is 1, minus the top times the derivative of the bottom, which is 1, all over 1 plus t quantity squared. This can be written as 1 over 2 radical 1 plus t. This cancels out to give me 1, so it's 1 over 1 plus t squared. If you divide by a fraction, you multiply by the reciprocal. So I'll just multiply this thing by 1 plus t squared. So 1 plus t squared over 2 radical 1 plus t. This is like 1 plus t to the half. So 1 plus t squared divided by 1 plus t to the half. Best final answer is 1/2, 1 plus t to the 3/2, and that's pretty much about it. All right, number 3. Language. Find the equation of the tangent line to the curve at the point corresponding to the given value of the parameter. All right, just like Calc 1, right? Remember in Calc 1, find the equation of the tangent of the curve at blah, blah, blah. So 3, They give you x as a function of t. They give you y as a function of t, and at t equals -1. So first thing I'm going to do is plug in t equals -1 to find a point. If I plug in -1, that's 0. Plug in -1 here, that gives me 0. So in other words, I think I'm at the origin. So here I go, plug in -1. I'm at 0, 0. Can't get any better than that. All right, so by formula, dy dx is dy dt divided by dx dt. Again, put that in your next cheat sheet. So that should be easy. Dy dt is 4t cubed plus 1. Dx dt is 3t squared. Plug in -1. So -1, -4 plus 1 divided by 3 times 1. -3 over 3, which is -1. Okay. Slope of -1 going through the origin, y equals -x. So y equals -x is the equation of the tangent to the curve. Okay, that's all. So hopefully not too big a deal. Okay, I'm jumping all the way to 15 because I wanted to. Find dy dx and d squared y over dx squared, first and second derivative. For what values of t is the curve concave upward? Well, remember concave up in Calc 1 means the second derivative is positive, right? So we'll get to that. So x is t minus ln t, y is t plus ln t. Right, so dy dx is dy dt. So what's the derivative of this? 1 plus 1 over t. Divided by dx dt. What's the derivative of this? 1 minus 1 over t. Make it look nicer, multiply top and bottom by t. So t plus 1 over t minus 1. Now, d squared y over dx squared, the messy formula. I've written it here again, but that's what the text gave. Page 649 at the bottom. Again, it looks scary, but the top is the derivative of dy dx. The bottom is dx dt. You already did that. So I'll show you what I mean. So where am I? Second derivative. Okay, the bottom is dx dt. Here's dx dt. I already did that. So just copy 1 minus 1 over t. The numerator is the derivative with respect to t of dy dx. In other words, just take the derivative of this. So I differentiate this with respect to t. The bottom, I just copy 1 minus 1 over t. Okay, so this is the quotient rule. Bottom, t minus 1, times the derivative of the top, which is 1, minus the top, t plus 1, times the derivative of the bottom, which is 1, all over t minus 1 squared. Okay. I rewrote this as t minus 1 over t. A little bit cleaner, right? 1 can be thought of as t over t. Like that. T over t minus 1 over t is t minus 1 over t. The top here comes out to be -2. T minus 1 minus t minus 1. The t's cancel out. I get -1 minus 1, which is -2. Okay, if you divide by a fraction, you multiply by its reciprocal. So -2 over t minus 1 squared times t over t minus 1. So -2t over t minus 1 cubed. All right, then it asks for concave up. Concave up means this second derivative is greater than 0. So I need to ask, when is this thing greater than 0? So you might recall in your intermediate algebra, you could do a sign analysis. Okay, so what makes the numerator 0? 0. What makes the denominator 0? 1. And I split into 3 regions. I test the point on this side, in the middle and on this side. Okay, so if I plug in -1, put a -1 here, -2 times -1 is a positive. -1 minus 1 is -2, cube it, it's negative. Positive divided by negative is negative. So this region is negative. And something between 0 and 1, 0.5, remember doing something like this in your intermediate algebra, right? -2 times 0.5 is a negative quantity. 0.5 minus 1 cubed is a negative. Negative divided by negative is a positive. So positive. And something in this region like 2. -2 times 2, negative. 2 minus 1 is 1. 1 cubed is 1, positive. Negative divided by positive, negative. Okay. So second derivative negative means concave down. Second derivative positive is concave up. So this graph is concave up only between 0 and 1. Okay, so that's how that one works. Okay, so I wanted to show you that one. And now I'm going to go backwards and do number 11, which is, I think, a similar theme. Check myself here. Yeah, somewhat similar. Okay, same thing. Find dy dx, second derivative. Which values of t is the curve concave up? Okay, notice it may be difficult or even impossible to try to make this an equation with x in terms of y or y in terms of x. It's not that easy to eliminate the t here. But you don't need to. All right, x is this, y is this. Okay, dy dx by formula, dy dt divided by dx dt. It's not that hard. So dy dt, 2t plus 1. dx dt, 2t. I could leave it like this, but I think for taking the second derivative, it's much easier if you split it in two. I'm going to split it into 2t divided by 2t, which is 1. And then 1 over 2t, which is 1/2 t to -1. See, I like to differentiate this. I know the next step I have to take another derivative anyway, but the derivative of 1 is 0, so that kind of helps me there. And now second derivative, d squared y over dx squared. By formula, it's a messy formula. Put it on your formula sheet. It's d dt of dy dx. In other words, just differentiate this or this. This is easier, right? I don't have to do the quotient rule like over here. Divided by dx dt. I already did dx dt right here. So automatically the bottom here is just 2t. That stays the same. How about this one? I differentiate dy dx. Well, that derivative is 0. This one becomes -1/2 t to -2. Okay, and I have a property in algebra that this 2 right here on top can slide down with this other 2 and become a 4. Okay, how can I convince you of that? How about multiply top and bottom by 2? All right, 2 will cancel there. 2 times 2 is 4. And a t to -2 can slide down and become a t squared times a t, -1 over 4t cubed. Okay, so there we go. Now, concave up, it says. So when is a graph concave up? When the second derivative is greater than 0. So when is this expression greater than 0? I have -1 over 4 t cubed. This whole thing is going to be positive if t is negative, right? T equals 0 is not allowed. If t is any positive quantity, this whole thing is negative. And if t is any negative quantity, this whole thing is positive. So the answer is the graph is concave up for t less than 0. Okay. I am going to show you 15 star, which was in the previous edition, so you won't find this in our book, but it was a nice problem that I wanted to show you anyway. I'm not sure why the author decided to take this one out because I like this problem, but anyway. X is 2 sine t, y is 3 cosine t, was in the previous edition of the text. T between 0 and 2 pi. Okay. So do the same thing. dy dx is by formula dy dt divided by dx dt. Okay, so what's dy dt? Negative 3 sine t. Dx dt is 2 cosine t. And sine divided by cosine is tangent. So negative 3 halves tan t. Now, d squared y over dx squared. By formula, it's the derivative of this with respect to t. So derivative of negative 3 halves tangent t is negative 3 halves secant squared t. And I divide by dx dt. I just copy what I did over here, 2 cosine t. See that? Here's dx dt, just copy it. This 2 gets to slide down with this 2, becoming negative 3/4. Okay, cosine in the denominator means secant in the numerator. So I have a secant squared times another secant, so a total of secant cubed. All right, so when is this concave up? It's saying when is negative 3/4 secant cubed greater than 0? Well, it's sort of the same thing. This whole thing is positive if secant of t is negative. Okay, sorry about that mess up here, but this means negative 3/4 is negative. So I want secant cubed to be negative. That's going to happen when secant is negative. If a function is positive, its reciprocal is also positive. And if something is negative, its reciprocal is also negative. So the reciprocal of secant is cosine. Okay. And when is a cosine negative? Remember, we have all students take calculus. Some of you may have heard that memory trick for the SIGNs. In the first quadrant, all 3 sine, cosine, and tangent are positive. Second quadrant, sine is positive. Third quadrant, tangent is positive. Fourth quadrant, cosine is positive, and that means the other 2 are negative. So when is the cosine negative? Between pi over 2 and 3 pi over 2. So t is between pi over 2, 3 pi over 2. So that's the answer to that one. Okay. All right. Then let's see. I'm going to talk about something like what? 17? Find the points in the curve where the tangent is horizontal or vertical. And never mind about a graphing device. Okay. Horizontal tangent, vertical tangent. Okay. dy dx is dy dt over dx dt. Okay. Oh, your meeting will end in 10 minutes. Okay, so there's that thing again. Okay, horizontal tangent. Numerator is 0. So horizontal tangent, dy dt equals 0. And the denominator is not equal to 0. Vertical tangent, dx dt equals 0. And dy dt is not equal to 0. Okay. So vertical tangent, remember, for a vertical line, the slope is undefined. Undefined means the denominator is 0. Okay, so that means for 17, x is t cubed minus 3t, y is t squared minus 3. So dy dx by formula is dy dt divided by dx dt. So dy dt is 2t, dx dt is 3t squared minus 3. Okay, so horizontal tangent, just make the numerator 0. 2t equals 0, that means t equals 0. And plug in t equals 0, x is 0, y is negative 3. So at the point 0, negative 3, you have a horizontal tangent. Vertical tangent, 3t squared minus 3 equals 0. Make the denominator 0. Factor out the 3. This becomes t plus 1, t minus 1. So that gives me t equals -1 or t equals 1. And if you plug back in t equals -1, t equals -1, this gives me 2 comma -2. Plug in -1, -1 plus 3 is 2. 1 minus 3 is -2. And if I plug in t equals 1, 1 minus 3 is -2. And 1 minus 3 is -2. Okay. So I have 2, -2 vertical tangent, -2, -2 vertical tangent, and 0, -3 horizontal tangent. So the graph crudely looks something like this. So you can see, right? Vertical tangent, horizontal tangent, like that. Okay, let's see. Set up 25 for you, and then I think that's about all I'll do. I'm not going to try to log back on. 25, show that the curve x equals cosine t, y equals sine t, cosine t has 2 tangents at 0, 0, and find their equations. Okay. Go ahead and do that. Notice the graph touches the origin twice. So let's find dy dt and dx dt and take the ratio. dy dx by formula is dy dt. So first times derivative of the second, sine t times negative sine t, plus the second times derivative of the first, cosine t, all over dx dt, negative sine t. Okay, this comes out to be cosine squared minus sine squared all over negative sine squared t. I don't like the extra negative sign here, so I'm going to multiply top and bottom by -1. So sine squared t minus cosine squared t over sine of t. Okay, so it says the point is 0, 0. So how is that going to happen? Where both of these occur at the same time? Well, when I plug in pi over 2, cosine of pi over 2 is 0, and cosine of 3 pi over 2 is also 0. Okay. I could keep going multiples of pi beyond that, but I don't get anything new on a unit circle. So let's just see what happens. If I plug in pi over 2, the derivative is 1 minus 0 divided by 1. That's 1. Plug in 3 pi over 2. Sine of 3 pi over 2 is -1, but when you square it, it's 1 minus 0 over -1. So that gives me -1. All right, so that gives me y equals x and y equals -x. So here's a rough picture of what you have. So the graph does come into the origin twice, once with a slope of -1 and once with a slope of 1. And there we go. Okay. All right, so I've shown you a lot of problems here. I'll do more tomorrow, but I'm going to get bumped out in about 4 minutes. Okay, so maybe we'll have to put up with this the rest of the semester. But maybe you guys like it because that means I can't have a lecture longer than 40 minutes. Again, actually less because it's, again, so it starts right when I log on, not when I press record. So from now on, I'll try to start right at about 10 after rather than starting early, because if I start early, that counts toward the 40 minutes. So it looks like we're not going to have any more lectures longer than 40 minutes, but that's okay. Let's see how it goes. Okay, only 4 minutes left. Let me stop the share. Check the chat. Okay, so anybody else with a question, please? Otherwise, we're done for the day. All right, have a good day, and we'll see everybody next time. Okay, bye, everybody.